and notes for AP Calculus on the topic of integration by U substitution for indefinite integrals, and we'll also go over how to use integration when separating variables to find a particular solution. So U substitution is kind of like the chain rule for integration. And remember, the chain rule, when we use that for derivatives, is when we had a function inside. We had to multiply by the derivative function inside. And that's what usually U substitution is used for as well, is when there's a function inside, how we integrate or find the antiderivative. So I put the steps here at the top that we're going to be following as we go through these problems here. So it just kind of gives you guidance. So the first thing you do is you set U equal to part of the integrand. The integrand refers to this whole expression that you're integrating in. So it's a part of it. Usually it's a function inside of a function. And our goal with U substitution is to make the integral simpler so it's easier to integrate. So in this case, notice the function inside is 4x minus 9. So that's what I'm going to set U equal to off to the side. And it doesn't have to be the letter U. That's just the one that's commonly used. You could really use any letter other than the variable that's already in the expression, in this case, x. Can't use x. So then what this allows us to do, we still have the integral symbol. And then now we can write it as the square root of U. As we say, U equal to 4x minus 9. However, we don't just write dx there because then that wouldn't make sense. Then the variables wouldn't match up x with u. So the way we get the dx out of there is the next step. We find du dx, the derivative of what we say u equals to right here, and then solve for dx so we can replace it. So notice it goes y equals if you dy dx. That's why if it's u equals, it's du dx, derivative. And the derivative of 4x minus 9, the derivative of 4x is 4, the derivative of negative 9 is 0. So it's just 4 in this case. And then the way you solve for dx, you can get the dx out of the denominator by multiplying both sides by dx. So then we'll have du on the left side equals 4 times dx, and then to isolate the dx, if you just divide both sides by 4, we get dx equals du over 4. And that's what we can substitute in to replace the dx there. Now we have square root of u times du over 4. So now, notice now everything's in terms of u. We got to have du here as well as the square root of u. There's no more x in the problem. Okay. So, to make it easier to integrate now, remember one of the properties of integrals is you can pull out constants out in front. Because just like with derivatives, they just stay there. So in this case, notice we've got a 4 on the number. That's like a 1/4. You can pull that on the outside. That's just going to stay there when you integrate, just like when you take derivatives, the coefficients stay there. And then to make it easier to integrate, we can rewrite the square root of u. That's the same as u to the 1/2 power. So notice what we've done is we've taken a more complicated integral that we can't integrate like this and turned it into a simpler one, just u to the 1/2 we can integrate. That's the goal of U substitution, to make it easier to integrate. So when you integrate u to the 1/2, using the power rule for integration. Remember, you add 1 to the exponent. So that's going to be u, add 2 halves to that, gives you 3 halves. And then divided by 3 halves, same as multiplying by the reciprocal 2/3. And then don't forget we have our unknown constant plus c at the end. And then we can just simplify it a little bit. So here, notice the 2 divides into the 4 twice, so that reduces a little bit. And we can switch this into radical form. It's easier to work with, so we'll have the square root of u cubed over 2 times the 3 there is 6, and then plus c. But that's not quite our final answer, because remember, the original problem didn't have any u in it. It had x. So to get it back in terms of the original variable, the last step here, u is equal to 4x minus 9. We can substitute that right back in for u right there to get our final answer. So it'll be the square root of, now 4x minus 9 replaces the u, cubed over 6, and then plus our unknown constant c. So notice we went through the other steps there. We substituted the expression found in step 2 for dx. So we substituted du over 4 in for dx there. That step right there. Then we simplified the integral. So it's in terms of u, so we simplified it to be just u to the 1/2. And then we integrated, that was this part, u to the 3s over 3. And then finally, our last step was to substitute the original value of u back into the original equation. So the final answer is in terms of the original variable. Now is substituting the 4x minus 9 back in there. All right, let's take a look at a couple more here. So the next one, notice, is way too complicated to integrate it like this. So we don't have a quotient rule for integration. So again, you want to use U substitution. And you might think setting u equal to the numerator, but that x squared minus 1 is not really a function inside. It's not really inside anything. But notice the denominator, x cubed minus 3 plus 1, is inside because it's raised to the 6th power. So really the only thing to set u equal to would be the function inside x cubed minus 3x plus 1. And then the integral sign still stays there. For now, this x squared minus 1 stays on the numerator. But now in the denominator, we can replace that whole x cubed minus 3x plus 1. We set that equal to u. So now it's just u to the 6th. Okay. But again, we need to get this dx out of there. Eventually, we need to get that x squared out of there too, but that'll happen later, you'll see. So initially, start by finding the derivative of what you set equal to. In this case, x cubed minus 3x minus 6. So du dx. Use the power layer, so the derivative of x cubed is 3x squared. The derivative of negative 3x is negative 3, and then we've got plus the derivative of 1 is 0. Constant. So again, we can solve for dx by first multiplying both sides by dx. And to do more of this, it's okay if you want to do some of these steps in your head here. If you get better at these. So the u would equal 3x squared minus 3 times dx. But notice we want to solve for dx here, so we can substitute in for the dx here. So we don't want to distribute the dx. Instead, we just want to divide by the 3x squared minus 3. So dx would end up equaling u over 3x squared minus 3. And that's what we can substitute in to replace the dx right there. So now we have, instead of dx, du over 3x squared minus 3. So it doesn't necessarily look that much simpler right now. And we can't integrate it yet because notice we've got two variables in there, both the u and some x's too. So if you use U substitution correctly, all the original variable, in this case x, should eventually cancel out. And here you can use a little factoring here. If we factor, notice we got a GCF of 3 out of the 3x squared minus 3. And let's see what happens when we do that. So then we'll have x squared minus 1 over u to the 6th times du. And then when you factor out the 3, look at what's left. As the GCF, we're left with x squared on the first term minus 1. And now notice we've got x squared minus 1 divided by x minus 1. So those reduce out to be 1. And now, to make it easier to compare, we can pull out the 1/3 as a coefficient out in front. And then all we have left is 1 over u to the 6th. But again, there's no quotient rule for integration. So remember, that's where we can utilize our negative exponents and rewrite it as u to the negative 6th. And then we have times du. So we've got 1/3. Then when you integrate u to the negative 6 using the power rule, that would be add 1 to the exponent, so u to the negative 5th divided by negative 5. And then plus our unknown constant c. And then we can simplify this, bring that u to the denominator, so it'd be 1 over negative 15, 3 times the negative 5, u to the 5th. plus c. Our unknown constant here for indefinite intervals. And then again, the last step here, we want to get back in terms of the original variable x. So we take our expression that we say equal to at the very beginning here, the x squared minus 3x plus 1, and substitute that right back in for u there to get our final answer. So it'd be 1 over negative 15. And then we just substitute that in, so it'd be x cubed minus 3x plus 1 to the 5th. And then plus c. That would be your indefinite integral, or also referred to as the antiderivative. All right, let's take a look at another one where it's a little bit different. Okay, so here, you could try to multiply this out, rewrite this 4 times, multiply it out, and then distribute the 1 over x cubed. That would work, but that would take a really long time. So instead, let's try to make it simpler using U substitution again. And there's 2 things in parentheses, but notice only one of them is really a function inside. This 1 over x cubed, you might think of saying equal to that, but notice it's not really raised to an exponent or inside of a root or anything. So it's not really a function inside, but the 2 plus 1 over x squared, that is. That's raised to the fourth power. So that's the better choice with U substitution. The function inside is what we usually say equal to. So I say equal to 2 plus 1 over x squared. And then we can rewrite it as now u to the 4th. So we set that equal to u, but we still have this 1 over x cubed here. That's not gone. But again, we need to replace the dx by finding the derivative here. But in this case, to make it a little easier to find the derivative, I'm going to rewrite this. The 2 is staying the same. But so we don't have to use the quotient rule on 1 over x squared. We can write that as x to the negative 2. And so now when you find the derivative, du dx, the derivative of 2 is 0. And then you can just use the power rule, bring down the negative 2. So it'll be negative 2 x to the negative 3. And then to solve this for dx, what I would recommend is make it a little simpler, is to first get rid of the negative exponent. So you can first rewrite this as negative 2 over x cubed. And then when your derivative is a fraction, it tends to be easier if you cross multiply to help you solve for dx. So notice we go negative 2 times dx. Negative 2 dx equals x cubed times du. And then divided by negative 2, you get dx equals x cubed du over negative 2. And then we can take that and substitute it into the dx. Right. So we'll put in our x cubed du over negative 2 and then try to simplify it. So again, we want all the original variable to be out of there, the x, and it all be in terms of u. And notice what happens, the x cubes reduce out here, which is what we want to happen. And then to make it simpler, you can pull out this coefficient of negative 1/2 out in front. And all that's left now, we don't have to rewrite it, it's already in a form we can integrate easily, is u to the 4th. So now we can integrate that. So you have negative 1/2. When you integrate u to the 4th, you get u to the 5th over 5, plus our unknown constant c. And again, you can just substitute in. Sometimes if you've got a more complicated expression for u, I'm going to pull this negative 1/10 out in front. And then substitute the u back in, which in this case was 2 over 1 plus x squared. Substitute that back in for u. So it'll be negative 1/10 and 2 plus 1 over x squared to the 5th plus our unknown constant c. So again, that would be the antiderivative or indefinite integral. All right, let's take a look at a couple more that are a little bit different now. So these, notice, we start out with the integral expression already. But sometimes we might use integration to do what's called solving differential equations. And the technique we're going to use, the first thing we have to do is separation of variables. So this is when you actually start with the whole derivative expression. And when it says find the particular solution, y equals f of x, notice first thing that is telling you is that it's a function, y is a function of x, right? To the given differential equation with initial condition f of 1 equals -2. We'll see where that comes into play. So what this really means, a particular solution, we're starting with the derivative, dy dx, and the particular solution, we're trying to get back to the original equation. And the variable we always solve for is the one on the numerator, in this case y. Notice it does tell you it's y equals also. So the first thing you have to do is, step one, separate the variables using multiplication and or division, so that each side of the equation contains only one variable. So in this case, we've got to separate the x and the y's. So first thing we can do here is to get the dx on the other side, we can multiply both sides by dx, like that. So we'll have dy equals y cubed x minus 2 dx. So that separated the dx from the dy, but the variables are not separated yet because notice the y cubed is on the right and the dy is on the left. So those need to be on the same side. X's are on the same side, both on the right side of the equation, so that's fine. So again, you're just using multiplication or division to separate the variables. So in this case, you can just divide both sides of the equation by y cubed. And once you get them separated, our next step is going to be to integrate both sides of the equation. So rather than writing this as dy over y cubed, here's again where we can utilize our negative exponents. Let's rewrite this as y to the -3 times dy equals, what's left on this side is x minus 2 times dx. So now the variables are separated, the y's with a dy, the x's with a dx, and now we're all set for the next step, once you get them separated, is find the antiderivative or integral of both sides of the equation by integrating both sides. Okay? So now we're going to integrate both sides. So you integrate y to the -3, you add 1 to the exponent, so y to the -2, and divide by the exponent, divided by -2. Now, on this one, you technically would have a plus c on this side and a plus c on the right side, but there's no need to have two different unknown constants, plus c, because you could always combine them to be a single unknown constant on one side of the equation. So really you could put the plus c on either side, it doesn't matter. However, since we're going to be solving for y, getting the y by itself as our final answer, that's what the solution is going to look like, y equals something. It will be easier and fewer steps to solve for y if we put the plus c on the side that we're not, of the variable we're not solving for, in this case the x. So I'm going to put in plus c on the right side instead. So when you integrate x minus 2, notice we don't need to use substitution here, it's not inside. If it was x minus 2 to the 7th or something, it would have been not here. So you can just integrate each one separately since they're just subtracted. When you integrate x, you get x squared over 2, minus when you integrate a constant 2, which becomes 2x, and then we'll put our plus c, our unknown constant. Alright, then there's a little simplifying we can do on the left side, so this would be 1 over -2 and then y squared, you go to the negative exponent. And now, we need to find what that unknown constant is. So the next step, find the value of the constant c by substituting in the initial condition. So if we weren't given a point on the original function, which is what this is, f of 1 is -2, we would have no way of figuring out what this constant is. But because we do have this point, this is the point 1, -2, there's our x and y. We can take that and substitute that in for x and y. x there and there, and the y right there, to help us solve for what c has to equal. So we do that. I'll put it right here. So I have 1 over negative 2. Y is negative 2, so negative 2 squared equals x is 1, so 1 squared over 2 minus 2 times 1 plus c. And now let's solve this for c. So let's see, that negative 2 squared would be 4 times negative 2 is negative 8, so this is negative 1/8 here. Equals 1 squared is 1 over 2 minus 2 plus c. So we have negative 1/8 equals 1/2 minus 2. Well, that's like minus 4/2. Gives you negative 3/2. And then to solve for c, add 3/2. But to make it easier to solve, to combine these, let's get a common denominator of 8 in this case. So you multiply 2 by 4, you get 8. So 3 by 4 would be 12/8, as the same as 3/2. So negative 1/8 plus 12/8, we get a c value of 11/8. So now we know what that constant is. Okay. And then we substitute that in for c right there. Because now we know what c is equal to. Okay. So now we have is 1 over negative 2y squared equals x squared over 2 minus 2x, and we just figured out c is 11/8. So now we have the equation, but it's not quite finished because it's said y equals f(x). It's not in function form yet. So our last step is to solve the differential equation for the variable that appears on the numerator of the derivative in the differential equation. Right, so the variable that's on the numerator in this case is y, so we're solving for y. It says y equals f of x. So there's different ways to go about it. Notice the y is on the denominator of this fraction. So we need to get it out of there. But you first might want to get it separated from this negative 2. So I'm going to first multiply both sides of the equation, everything by negative 2. So that'll wipe this out on the denominator here. So we'll just end up with 1 over y squared on the left side equals negative 2 times x squared over 2. The 2's reduce out, and you just end up with negative x squared. Negative 2 times negative 2x is positive 4x. And negative 2 times 11/8 is negative. And 2 goes into 8 4 times, so negative 11/4. And now, to get that y squared out of the denominator, we can multiply both sides by y squared. So that way the y squared is reduced out here, and we're just left with 1 on the left side. But I'm not going to distribute the y squared like I did the negative 2 on the right side, because we want to solve for it. So it's actually easier to solve for if you just leave it on the outside. Because now you can just divide both sides by this expression negative x squared plus 4x minus 11/4 to get the y squared by itself. So we'll have 1 divided by negative x squared plus 4x minus 11/4. And then to solve for y, take the square root of both sides. But remember, when you take an even root of both sides, you need plus or minus. So you need plus or minus. And you could leave it like this, or if something simplifies, nicely you can simplify. In this case, we know the square root of 1 is just 1 on the numerator, so that's just 1. But the denominator doesn't really simplify, so we'll just leave that So it looks like that's our final answer. However, there's one more thing. It's not quite right. It says this has to be a function. Remember, y equals f of x? But with a plus or minus sign there, remember the definition of the function is for every x value or independent variable, there's only one and only one corresponding y values. But with a plus or minus, if you plug in a certain x, you're going to get two different y values. So that would make it not a function. So, to make it a function, it can be the plus or the minus, but not both. And the easy way to figure out which one it is look back at your initial condition. Notice it was the y coordinate was negative. It was a negative 2. So that is what tells us that it's the negative, not the positive. If the y coordinate in the initial condition had been a positive number, like positive 2, then we know it would be the plus instead. So that's all you have to do to tell which one it is, so if you have a plus or minus. You won't get it on every single problem, just the ones you have to take an even root of both sides on to solve for y. So this would be our particular solution. And now as a function, y equals negative 1 over square root of negative x squared plus 4x minus 11/4. All right, let's take a look at one more of these separation of variable problems. This one's a little different because it's got different letters in it, basically, and it's worded a little different. So it says, given h equals 16 at time t equals 0, where h is the height in inches of the water in the container and t is the time in minutes, solve the differential equation for h as a function of t. Okay, so it says we're solving the differential equation for h, which this is again in variable on the numerator, as a function of t. So we first have to separate the variables. So we're trying to get back to h, and we just have the derivative dh dt. So when you have the derivative, it's already a fraction, then you can cross multiply is probably the easiest way to help you start to separate the variables. So when we cross multiply this negative out in front, we have to decide if it's going to be with the 2 or with the square root of h. I'm going to put it with the 2. So we get negative 2 dh equals square root of h times dt. But notice when we do that, the variables are not separated correctly, right? Notice this problem, there is no t, which is fine. If there were, it would have to be on this right side with dt. But there is an h, square root of h, but it's not on the correct side. It's with the t, it needs to be with the dh. So again, you just divide both sides by square root of h. So alleviate that. And remember, our next step is going to be to find the antiderivative to integrate both sides. So negative 2, we can rewrite this as h to the negative 1/2, make it easier to integrate, times dh, equals, all that's left on this side is just dt. And now we can integrate both sides, and when you do that, since the negative 2 is the coefficient, you can actually leave it outside the equation. It's going to stay there. So when you integrate that, the negative 2 stays there. When you integrate h to the negative 1/2, using the power rule for integration, you add 1 to the exponent, add 2 out, so you get h to the positive 1/2. Divide by 1/2 is the same as multiplying the reciprocal, which is just 2. Again, we're going to have a plus c. On either side, you can choose. Since we're going to solve it for h, I'm going to put it on the other side. It doesn't have the h on it to make it easier. Now, how do you integrate it if it's just dt? Well, remember, even though we don't see it, in front of that dt is an invisible 1, right? So we do 1, and that's just going to give us 1, and this tells us the variable's t. So that just integrates to dt plus our unknown constant c. And then we can combine these to be negative 4, and then square root of h equals t plus c. So now we've integrated both sides. Now we can substitute our initial condition, which is given a little different form here. It doesn't call it the initial condition, but it says h equals 16 at time 0. So notice we can substitute that in. H is 16 when t is 0. So it'll be negative 4 square root of 16 equals 0 plus c. So square root of 16 is 4 times negative 4 gives you negative 16 equals c. So there's our constant. And then we take that constant and substitute it right back in here before we substitute in our point. So now we've got negative 4 square root of h equals t plus c, but we know c is now negative 16. And the last step is to solve. It says solve for h, but notice you can, even if it didn't say specifically which one to solve for, it'd be the one on the numerator, h. So here to get the h by itself, you divide by negative 4 first. So we'd have square root of h equals t minus 16 over negative 4. And then last step to solve for h, square both sides. Notice here we don't need plus or minus. If you square something that's not plus or minus, it's just going to be positive. It's only plus or minus if you take an even root of both sides. So we get h equals, and then you can square out the t minus 16 or just leave it like that. It's t minus 16 squared, either way. The denominator you might want to square out because that's simple. Negative 4 squared is just 16. And that would be our particular solution, our solution for the differential equation, our final answer. And notice what this gives you. It tells you what the height of the water is in the container at any specific time. So if you want to know the time after 3 minutes, you'd substitute 3 for t and it'll give you the time. Also, if you wanted to know the time when the container is empty, you could set h equal to 0, and notice that'll give you t equals 16. After 16 minutes, it ends up being empty. And that concludes the notes for AP Calculus on the topic of integration by U substitution for indefinite intervals and solving for the particular solution using separation of variables.